Hello everyone again. Just a couple good chemistry jokes to get us started. So the first one is, why shouldn't chemistry students drink water in class? Because it will decrease your concentration. And what's another way that you can decrease the concentration of ions in a solution? You can form a precipitate. So remember, if you're not a part of the solution, you're part of the precipitate. All right, let's get started. So our essential question today is, how does cell potential respond to changes in concentration of a product or a reactant? So today it's all about changing concentration of the chemicals in a cell. So first, let's check out how Q, or the reactant quotient, is going to be important today. So Q, or the reactant quotient, tells us the ratio or concentration of products divided by reactants at any given point in a cell. And remember, if there are exponents, those are included as well. So under standard cell conditions, or E with the degree symbol, this symbol right here is the symbol of standard conditions. The concentration of reactants and products are both initially 1 molar. So if I have 1 molar for products divided by 1 molar for reactants, Q would be equal to 1, and the actual voltage of my cell is equal to the voltage of standard conditions. Here's an example of zinc solid reacting with copper ions to form copper solid and zinc. Over here is showing a kind of animation of the cell that's happening. So over time, as this cell is running, while the concentrations initially started at 1 molar, they will change over time. The reactants will decrease over time. So as you can see, the zinc reactant is reacting away, forming the zinc ions. So my concentration of my reactants is going down, and the concentration of my products is increasing. As the cell runs, the voltage will progressively decrease over time. Eventually, the cell will reach equilibrium, and at that point, the value of the cell potential becomes 0 volts. The battery is now dead, and delta G equals 0. So again, Q, that reactant quotient, is products divided by reactants. So over time, reactants are decreasing in solution. My zinc is reacting away, my copper ions are getting reduced, and my products are increasing. I'm forming more zinc ions and I'm forming more copper solid. So Q increases. Q becomes very large, or greater than 1, as the concentration of my products, my zinc ions, and the concentration of my reactants, copper ions, decrease and eventually get to 0. Eventually then, the Q value is equal to K, and like I said, the battery is dead. Because K is also very large, this reaction is spontaneous in the forward direction. K is actually like 1 times 10 to the positive 37th. It's crazy large. So this is a forward reaction. So as Q increases, it gets closer to the value of K. This chart summarizes what's happening here. So over here, I have my copper ions, positive 2, 1 molar. My zinc ions, 1 molar. Q is equal to 1 to start. My voltage is at that standard voltage, 1.1. My delta G is negative. It's favored in the forward direction, spontaneous, and my K is large. This is a product favored, forward direction favored reaction. As this reaches equilibrium, my concentration of my copper ions, or my reactants, have decreased. The concentration of my products, or my zinc ions, have increased. So Q now becomes very large, or equal to my K value. So my voltage is 0 and my delta G is also 0. So now we're going to look at non-standard cells. So E with no degree symbol, where it's not 1 molar, and looking at how does changing concentration affect that cell potential. So the value of E under non-standard conditions can be calculated using an equation called the Nernst equation, where E is equal to non-standard conditions and E with the degree symbol is equal to standard conditions, or 1 molar. Here's the equation. So again, E cell is non-standard, or any concentration other than 1 molar. E standard is at 1 molar. Minus R is the gas constant, T is temperature, N is moles of electrons, F is Faraday's constant, times the natural log of Q, where again Q is products over reactants. So really this part right here is just a constant, it's just a number, and this equation is on your equation sheet. So how does changing the concentration of a reactant or product affect Q? So once again, Q is equal to 1 when products are equal to reactants. If Q becomes greater than 1, that is because either the concentration of the products have increased or the concentration of the reactants on the denominator have decreased. If Q becomes less than 1, the concentration of the reactants on the denominator have increased, or the concentration of the products have decreased. So here's how this affects the cell potential and the voltage of our cell. So this is a situation where Q is less than 1, which again means I've increased the concentration of my reactants, or I've decreased the concentration of my products. So in this first example, my reactants have increased. I've added more copper ions. Q is now less than 1, and if you'll notice, the voltage is now greater than what it was before. It used to be 1.1. When I decrease the concentration of my products here, my zinc concentration is 0.01, Q is again small, and my voltage is higher than expected. Here's the opposite. This is what happens now when Q is greater than 1. So I increase either the concentration of my products, zinc, or I decrease the concentration of my reactant, copper. My voltage now is lower than expected. So here's the summary of what's going on. Increasing the concentration of reactants or decreasing the concentration of products increases that driving force for the reaction, resulting in a voltage that is greater. If Q is less than 1, you're now moving further away from equilibrium where the battery is dead, and therefore E will be bigger. So remember, equilibrium has a very high value. If you decrease the concentration of reactants or increase the concentration of products, this decreases the driving force of the reaction. Therefore, your voltage will be smaller. If Q is greater than 1, you're getting closer to equilibrium where your battery has dying, so your voltage is decreasing over time and will be less than the standard voltage. This should hopefully make sense. The more reactants that you have, the more it's going to continue to move in that forward direction, creating the voltage, creating the electricity. The more your reactants get depleted, the less that this is going to happen. Here's a summary of this information in chart form. Don't know where to put me. There you go. So again, at standard conditions right here, that's where E is equal to E standard. Q is equal to 1 and reactants and products are the same. When Q is greater than 1, the cell is closer to equilibrium than before at standard conditions, and this is because I've either increased product or decreased reactant. And over here at equilibrium, again, where E is equal to 0, that's where Q and K are equal to each other and the cell is dead. The farther I move away from that equilibrium spot, my voltage will increase. The cell is farther away from here at equilibrium because I've either increased the amount of reactant or decreased the amount of product. So what we're doing is we're changing the aqueous substance in my Q expression. So remember, solids are not included. And so we have to think about, how am I changing the concentration? Remember, we can decrease the concentration by adding a precipitate or diluting the solution, or you could continue to add a greater concentration of the ions, dissolve more than was before. So what we just did is we looked at a qualitative approach. Now this is a quantitative approach using the Nernst equation. So this is for all the math people out there, and this is a very helpful thing to do on the test. Now that the Nernst equation is included, this will be even easier. So there's 4 situations that can happen. The first is where products decrease. So let's say I change my products to 0.5 molar instead of 1. Now my Q is less than 1. And if you take the natural log of any number less than 1, it will be negative. In my equation, I have a negative then times a negative, which ends up being a positive, and so I'm adding some positive number to E cell, and my voltage will increase. If I increase the concentration of my products to 2 molar, the natural log of this, a number greater than 1, will be positive. So now I'm subtracting a positive number, and so my E cell value that I'm calculating here will be less. If I increase the concentration of my reactants to, say, 2 molar, now my Q is again less than 1. If I take the natural log of a number less than 1, it will be negative. A negative times a negative is positive, so my cell value goes up. And lastly, if I decrease the concentration of my reactants to 0.5 molar, my natural log of a Q of a value greater than 1 is positive. If I subtract a positive, E decreases. So it's also helpful to be able to do this quantitative analysis. Now you will continue on with part 3, applying this information to the simulation where you will create some non-standard cells.